In this video, we're going to be looking at the concept of acceleration. What are we going to be doing? We're going to define the term acceleration. We're going to look at the types of accelerations and their causes. We're going to compare and contrast average acceleration to instantaneous acceleration. We'll learn to calculate average acceleration and how to estimate an instantaneous acceleration from a graph. We're also going to look at the equations for accelerated motion and look at some problem-solving strategies that can be used for solving those questions. Why are we doing this? Well, simply because most motion in the universe is actually accelerated. And only by looking at accelerated motion did we learn, and this is how we learn what the laws of the universe are. Acceleration is all about change, and life is change. So by understanding the relationship of acceleration and what causes it and how it applies to motion helps us develop skills that we need to understand the relationships that change our everyday lives as well. In the past, we've looked at motion with a constant velocity, which means a constant speed and a constant direction. Nothing in the motion changes. An example of that is when I have an object that slides on smooth surfaces, such as ice, if the surface is flat. So here we have a hockey player who is sliding across the ice, which is very, very smooth. And if there are no forces affecting their motion overall, then their motion remains constant, which is why we say that they will travel the same distance every second. So if they travel a distance of x in 1 second, the next second they travel the same distance, same distance, same distance. So if this was 4 meters, it's 4 for all of these, which makes their motion easily predictable. Now, according to Newton's first law of motion, an object in motion, or a system, does not change its speed nor direction of that motion unless there is a net unbalanced force, an external force acting on that object or system to change the motion. And if we look at a free body diagram of the forces acting on this person, we know that there's gravity pulling the person down and the ice is pushing the person upwards. And these two forces have to be balanced out, because if the ice pushed up more than gravity, the person would be flung up into the air. And if gravity pulled down more than the ice was able to push up, the person would fall through the ice. So these two forces are balanced out, which means they cancel. And so if we were asking the question, why doesn't the person's motion change? We could actually reply that with another question saying, well, with all the forces cancel out, why would there be a change? There's no external influence causing the motion to change. And Newton's first law is mathematically expressed as the second law, where the net external force acting on an object or system is equal to the mass times acceleration of that object or system. But if there is no net external force, then there must be no acceleration as well. So an object in motion will maintain the same speed and direction because there is no external unbalanced force acting on it. But if there was a net external force, then there would be an acceleration. If we take a look at a case where a car accelerates from rest, speeding up as they take off, for example, in a racing strip like we see right here, we see that the distance that the car travels each second changes because it is moving faster. If the acceleration is constant, we see a very distinct pattern. It's governed by what we call the law of odd numbers. Whatever distance I travel in my first second, I will travel 3 times that distance in my second second, 5 times that first distance in my third second, 7 times the first distance in my fourth second, and so on. So if I was to have traveled a distance of, let's say, 2 meters in the very first second, then I would travel 6 meters in the next second. and I would travel 10 meters in the next second after that. Now, this 10 is not from the starting point, but only from where I am for that 1 second. So the distance here would be 6, then, sorry, 2, then 6, then 10. So the total distance traveled would be 2, then 8, then 18. If we look at the forces acting on the car, we see, just like with the person on ice, we have the force of gravity and the force of the road, which was like the force of the ice. Again, we know that these two forces have to be equal because the cars are not popping off the road nor falling through the road. So these two forces must be canceling each other out. But there is also going to be another force acting on the car. The roads are rough. As the tires try to move backward, the road will push those tires forward in reaction to the tires' force on the roadway. This force is a friction force, so friction is actually propelling the cars forward. But this is unbalanced. There's nothing here really to fight it or equal it out. And for that reason, I do actually have a change in speed because according to the first law of motion, there will be a change in speed if there is an unbalanced external force acting on it to cause the change in motion. And that is exactly what we have right here. If we take a look at Newton's second law, which is again the mathematical representative of the first law, I do have a net force, the force of the friction of the road. So that must equal the mass of the car times the acceleration. Since this force of friction is not zero, there must be an acceleration which causes the speed of the car to change. However, there could also be another type of acceleration that we're going to look at later on in the course, where the speed does not change, but rather the direction changes. This is a case of where we have a satellite orbiting the Earth. If we were to ask the question, why do satellites orbit the Earth? Most people will just say, well, it's gravity, because the Earth's gravity pulls on the satellite. And that is actually very correct. That is the only reason why the satellite orbits the Earth, is because there is a force pulling on the satellite. But since there is no force pulling against gravity to fight it, there is an unbalanced force, which is why the satellite changes direction. This type of force, in this particular scenario, does not cause the speed to change. The satellite will keep the same tangential speed, but the velocity changes because of the change in direction. This particular type of acceleration is not going to be our focus right now. We're going to look at the ones that change the distances traveled every second, the one that affects the speed, not the direction right now. But it's important to recognize that this is a type of acceleration and it's going to be governed underneath the same rules as the acceleration that we're looking at now. So let's talk about translational acceleration, specifically average acceleration. We know that acceleration by definition is the change in velocity over time. It's the rate of change of velocity. If I have a velocity versus time graph, then the acceleration would be the slope of the velocity versus time graph, which is, of course, then the change in velocity over the change in time. One of the major purposes of knowing an object's acceleration is to predict the future, to find out how fast something will be moving later on, or how much time does it take to reach a particular speed. So we can easily rewrite this equation, solve for v final, by simply multiplying both sides by t. And then adding over the initial velocity. When we do that, we see the equation v final equals v initial plus at. By the way, If this was a math class, we would be turning around and saying that we're saying that y final, which is my final velocity, is equal to y initial plus the slope of the line times the x-axis. Now, my initial y velocity is often denoted by the letter b in math class because that's my y-intercept. And then, since we're using the letter b for the initial y, we can drop the f for the final y and just call it y. Now, for those of you guys who are really big into math, you might recognize this as actually just y equals mx plus b equation, which makes perfect sense because the graph itself is a straight line. And the mathematical equation for a straight line in the xy axis is y equals mx plus b. You will notice that physicists will often write our equations backwards compared to how a math person would write the equations. And the reason for this is focus. As a mathematician, I want to know what the power of the equation is so I can know immediately what kind of mathematical strategy I need to employ. So here I can see that the exponent on the x is 1, so I know that this is a linear equation, and I can use all my linear strategies, and I would never even bother using a quadratic because it's not a squared power. As a physicist, we are not interested so much in the mathematical property of the equation. We will use it, but we're not going to focus on it. Our focus is on what does the equation represent. And so we have to make sure that everything meshes out. So I'm dealing with velocity. So everything should check out to be a velocity. So the very first thing I see is velocity. No, velocity equals velocity. That makes perfect sense. Plus, now acceleration times time. Well, acceleration times time is a change in velocity. So we're really saying here that my final velocity equals my initial velocity plus my change in velocity. So we often write our equations backward from a math teacher. But it doesn't matter which way you write it, the outcome will always be the same and the mathematical strategies will always be the same as well. When looking at the velocity versus time graph, we can also see on how the displacement of the object is going to change and why it increases by a rate that is equal to that follows the rule of odd numbers. Remember, for a velocity versus time graph, the area equals the displacement or the change in position. If I take a look at this triangle and I look at the area that is completed for 1 second, I can very easily see a triangle. So that would be the displacement traveled in 1 second. That's my distance x. In my next second, I will not form a triangle. I'd get a triangle from 0 to 2 seconds, but from 1 to 2 seconds, I actually form instead a trapezoid. And that trapezoid has the equivalence of 3 triangles to it. We have the triangle on the very top that's equal to the first triangle that we have. So this triangle and this triangle are identical. And then I have a rectangle that has the same height as my first triangle. But a rectangle is really just 2 triangles. So I really have 3 triangles of identical size. Now, if my first triangle here was a distance of x, then the total distance or area of this trapezoid would be 3x. In my next second, I have an even larger trapezoid, where the top triangle is identical to the top triangles in the other seconds before it, and I now form a rectangle that is the height of these triangles here. So I actually now form a rectangle, though, that's composed of 4 triangles. So here I have a total area of 5 x's compared to the very first x from the first second. So here we again see the rule of odd numbers as it relates to the area underneath the velocity versus time graph and the displacement traveled every second. Not all motion that's accelerated will be as simple or straightforward as a car accelerating in one direction, constantly speeding up following the rule of odd numbers. In some cases, we'll have something that's very complicated, such as an object that is oscillating on a spring, where it bounces up and down. Here we can see that the velocity is always changing. Not only is the velocity always changing, but it's changing both magnitude and even direction. And the rate at which the velocity changes also changes. If we take a look here at the velocity graph for this block that bounces up and down, we can see that the slope, which is the acceleration, changes. It has a slope that's positive and steep, and then it goes to zero. Then it goes negative and shallow, negative and steep, and then it keeps changing. Because of this, we cannot use the velocity equation, v final initial plus acceleration times time equals my final velocity. That won't work here because this was on the condition that the acceleration is constant. Remember, this equation is really y equals mx plus b in disguise for a math class. And this only works for a straight line graph. This is not going to be that circumstance. So we can never use this type of equation. It's also important to note that since the acceleration is always changing, it's not necessarily convenient to work with an average acceleration that represents the entire motion. And that is very true if we are interested in what an object is doing at a particular time. So if I want to know what was going on at this particular moment only, I don't want to know about the average acceleration for the entire trip. What are you doing now? You might have had a conversation like this in the past with perhaps your parents or a teacher where you might have a pretty solid average, but there was a test or something that did not come out very well for you, and you're having now a conversation about this grade, and you might turn around and say, well, my average is really good, and we're not talking about the average. We're talking about this test because that affects what the average can be. That's what we see here, a very similar circumstance. Yes, there's an average value for the acceleration that represents what's going on for the entire motion, but at this particular moment, that average doesn't matter. We want to know what's going on right here. And if I was to take a look at the slope of this line, that would be the acceleration at that moment. Recall this acceleration at a single moment, the instantaneous acceleration. Instantaneous because it's at that instant, and it can change. If I have a graph like this, my instantaneous accelerations are always the same as everyone, so it makes things very easy to just call it an average because every single point has the exact same acceleration. So it's the case of where Bob gets an 80 on every single assignment and every single test and every single quiz. You know what? You take any random piece of his work, it just represents everything for the entire year because everything is constant and it's very easy. However, for most people, that's not the case. Our averages are based on a myriad of different values, and grabbing any one assignment at random definitely does not give you a picture of what the person is doing overall. And that's what we see here. So if we wanted to find the acceleration at a particular moment, we'd have to be able to find the slope of a graph at a single point. Now, the major way we do this is through calculus. So we are not going to be focusing on doing that. However, we would be expecting you to recognize that the acceleration here would be much greater than the acceleration here, because if I look at just what the tangent line slopes are, I can definitely see that this is a slope of 0 or close to 0, and this one here is a positive. If we were to ask if the object was moving backwards or forwards, we'd expect you to be able to take a look at the, I'm sorry, if the acceleration is causing the object to increase or decrease its velocity, we'd expect to be able to identify which way the slope was going to answer that type of question. When looking at a velocity versus time graph, if a person wants to find the instantaneous acceleration, which is the acceleration at one moment in time, and they do not have a working understanding of calculus, they run into a mathematical roadblock. The reason for the roadblock is the fact that acceleration is the change in velocity over time, and we often learn that that is the slope of a velocity versus time graph. But slopes actually come in two flavors. The first flavor is the average slope, and that's the one that we often work with where we have a change in y over a change in x. That's why we call the acceleration that we find by using the slope this way the average acceleration. Now, the slope average always requires 2 points. I need to have an initial y value, or an initial velocity in this case, and an initial time. And I have to have a final velocity and a final time. So some time has to pass by for me to see a change in velocity so I can figure out what the acceleration is for that passage of time. And since it's over a passage of time, there'd be several velocities or several accelerations along the way that could be changing. So we're finding the average overall for that change in time. Instantaneous, though, is at a particular moment only. I would have to find the slope of only 1 point. I would need delta x here to be equal to 0, or at least so close to 0 it's ignorable. This is one of the foundational skills that you learn in calculus on how to find what they call an instantaneous slope. Please note we call the acceleration off of, which is the slope off of this graph, the instantaneous acceleration when it's at a single point. Now, this is not a calculus-based class. We are not going to be using any calculus whatsoever, at least not unless you want to do it on your own. However, we should be able to estimate at least what the instantaneous acceleration is going to be based off of the pattern that we have on the graph. Now, the way that we do this is we find the average acceleration that is closest to this point that is possible. So if I had to estimate the instantaneous acceleration for this point, I would pick 2 points that were equidistant in terms of the time from the point, and I would have them as close as I could where I can get accurate values off the graph. So I'm going to get the slope closest to this. So my goal is now actually to find a line that is going to be as parallel as possible to the green line. So if I wanted to estimate this and I was to pick this point and this point, that would definitely be totally inappropriate. Both points are very far away, and this is not in the middle of those 2 points. Please notice I have a slope here of 0 for the purple line that I just drew, while green is definitely not. The blue line that I have here isn't exactly parallel, but it's a lot closer. And so for an estimate, I would be okay with that. If I could come up with 2 points that were much closer and pick those 2 points, then that line is going to be even more parallel, and I would use that. So at our level, you will not be required to calculate the instantaneous acceleration from a graph. However, you should be able to explain why you can't, and you should be able to at least estimate what that value would be. So again, no calculus is required, although we should be aware that that is what would be required to find the instantaneous acceleration. And we would expect you to be able to use the average acceleration to estimate the instantaneous. And if someone was to ever just challenge you saying, well, why can't you find the instantaneous acceleration? Just turn around and say, well, we have for an instantaneous acceleration, we need to have a change in time of next to zero, which requires calculus, and we aren't doing the calculus. We are algebra based, and that's really all you have to worry about for something like this. Remember, when looking at slopes, which are actually vectors, positive and negatives do not mean to gain or lose. They rather mean just direction. If my velocity is positive and my acceleration, which is the slope of my velocity versus time graph, is also positive, then I am speeding up, which we can see right here. Now, some people say positive slope, so it must be speeding up. But please notice, in the section where I have a positive slope and negative velocities, I am actually slowing down. And that's because my velocity is going to the left while my acceleration is going to the right. Or if my velocity is going down, the acceleration is pulling up. While in this case, where I'm speeding up, my velocity and acceleration are in the same direction. So they're both moving up, they're both moving to the right. Likewise, here I have a negative slope, and I am slowing down, but not because the slope is negative. It is because I have a negative acceleration, because that's what the slope represents, while I'm having a positive velocity. My acceleration and velocity are in opposite directions. And that's why when I have a negative slope or negative acceleration right here, I'm actually speeding up, because my velocities are also negative. They are in the same direction and they are working together. So again, we have to be very clear on what the sign of the slopes represent, direction only. And when the acceleration and velocities are the same signs, they always speed up. When they are opposite signs, they always slow down. When just looking at the shape of the velocity versus time graph, we can also tell from the shape that the object is speeding up because the velocities are moving away from zero on this section. And as long as my velocity becomes further and further away from zero, it is speeding up. Now, one of the things that is very misleading for people is they can see the curve, so they're thinking slowing down. The acceleration, the rate at which the velocity grows, is getting smaller, but is still growing, just not as much as it was beforehand. When we reach this peak right here, that is where my velocity stops changing. So now all of a sudden, it would try and maintain a constant velocity, but now it is getting closer and closer and closer and closer to zero instead. So now I am slowing down on this section right here. Remember, to tell if something is speeding up or slowing down, you just have to look at the velocity graph and see if those velocities are moving towards zero or away from zero. So when looking at this type of graph, I can always see that sections like this one, where I'm moving away from the time axis, or sections like this one, where I'm moving away from the time axis, I will always be speeding up. In sections where I am going toward the time axis is when I'm going to be slowing down. And this is why I have to stress again, it's more important to understand what the graphs are telling us than trying to memorize everything for these different graphs. To slow down means that the velocity itself is approaching 0 meters per second, or the time axis, where it's traditionally going to be at the 0 meters per second. If I'm speeding up, then the velocity is moving away from 0. It doesn't matter if it's positive or negative. Remember, signs are just direction. They have nothing to do with size. When looking at the positions of an object, or where it is at a particular time as it is traveling with acceleration, it is important to note that while it's true the objects will follow the rule of odd numbers, we don't often look for the distance traveled in just one section, but rather the distance traveled for the entire time or a particular location. So I may not be interested in the fact that this object has traveled a particular distance from, let's say, 2 to 3 seconds. Instead, I just want to know where is the location of this object at 3 seconds in reference to my origin. So this distance here is not really as important to me as this distance here, which is the total distance traveled. So we will often look at the positions of the object. When we do that and we graph the motion of the object in terms of positions versus time, we will see a parabola taking place. And this means I have a squared relationship with time. Now, why on earth does it follow a squared relationship? Well, if we take a look at the distances traveled here, I can see that in 1 second, I traveled a distance of 0.5 meters. In the next second, I would have traveled a distance that's 3 times 0.5, which is 1.5 meters. So the total distance traveled, oops, sorry, put that in the wrong spot. So this here is 0.5. And so this would be 1.5 meters. So the total distance traveled would be 0.5 plus 1.5, so that's a total distance of 2. In my next instance, I'm going to travel 5 times the distance of 0.5. So 5 times 0.5 is 2.5. So the distance I would travel total is 0.5 plus 1.5 plus 2.5. That gives me a total of 4.5. And so on down the line. So if this was 1, this is 3, this is 5, this would be 7, and 7 times 0.5 is 3.5 meters. And 3.5 plus the 7.5 that I've already traveled comes out to be 8. So we will always see this parabola when I am accelerating, speeding up as I am traveling. Keep in mind that parabolas always have concavity. Concavity is the curviness of the graph. Concavities on a position versus time graph indicate the acceleration. If my concavities are positive, which means they hold water as part of a bowl, then I have positive acceleration. Does not mean the object is speeding up. It just means the acceleration is in a positive direction. And if my velocity happens to be in a positive direction, then I am speeding up, as in this case. And if my velocities are negative, then I would be slowing down, as I see in this case. Negative concavity is again when my curve would spill water, because I have an upside down bowl that cannot hold the water. Negative, again, is only a direction, does not mean I'm slowing down. Here I have positive velocities on a position versus time graph because I have a positive slope and I have negative concavity, so I am slowing down here, but I am speeding up on this one over here. Again, if I have straight lines, there is no concavity, and these are the graphs of no acceleration if this is a position versus time graph. And I know I have said this in the past, and I will be saying this many times over, because it is such an important concept and one that most people always overlook or have a hard time accepting. But the velocity of an object only increases, which means becoming faster, if the velocity and acceleration are the same sign, which means they're in the same direction. This means that the velocity only increases, becomes faster when the slope of the position versus time graph, which is the velocity, and its concavity which represents acceleration, or I should say is related to acceleration, are the same sign, because that means they are in the same direction. Velocity only decreases. It only slows down when acceleration and velocities are in opposite directions, which means they are opposite signs mathematically. Looking at position versus time graph, that means that the slope of the velocity time graph and its concavity are on opposite signs. Understanding that makes your life so much easier. So here again, we can see that everything is going to be speeding up. Please notice I have positive concavity, positive slope. I have a positive velocity because that's the slope. I have a positive acceleration. Here I have negative slope, negative concavity, negative velocity, negative acceleration, and everybody is speeding up. Here we can see quite the opposite. Here I have positive slopes, so I have positive velocities, but a negative concavity, which is why my velocity is approaching zero. And I can see right here. Likewise, here I have a positive concavity, so I have a positive acceleration, but my slopes are negative, my velocities are negative. So I can see that my velocities are slowing down yet again. From a velocity versus time graph, we can find the displacement of an object simply by finding its area. When I have a constant velocity, I form a simple rectangle that can be broken up into several smaller rectangles, all the same size. So for this case, I have an object that's traveling at a constant 2 meters per second. So I can see for every second of time, I can create a rectangle with that represents 2 meters traveled. The total distance traveled is the total area underneath the graph. So for 1 second, I've traveled 2 meters. For 2 seconds, I have traveled a total of 4 meters, and for 3 seconds, a total of 6 meters. When I graph my position versus time, I get a linear line because I have a constant rate of change. Everything is going to grow 2 meters for every second. In fact, my slope here is 2 meters per second because that was the velocity of the object as it travels. If I accelerate, my velocity does not remain constant. That means the area underneath the graph grows. It increases by the rule of odd numbers. And so I see a parabola being created in its place. But this parabola comes from the total area of this graph, just like the position here comes from the total area of this graph. So if I had to derive an equation or create an equation to find the position of an object to find the position of an object based on its velocity as it travels, I'd have to base that off of the area of the graph. At a constant velocity, my area would be that of a rectangle. So it would be height times base, or velocity, which is my height of the graph, times the time, which is the base. And so displacement is equal to the velocity times time. And we've done that in the past. And this velocity is going to be a constant, so we're going to say average right here, because I can't use that all the time. For example, if I look at this case, my velocity is not constant, so I can't go ahead and multiply any of my values just by the time. I have to find the area of this triangle, which is 1/2 the base times the height. So I can now turn around and say, well, height is the change in the velocity. So it's not even my velocity, it's the change in my velocity times my time. And so we have a very different equation here. It's the area of a triangle. However, this equation can be rewritten. We often think of the area of a triangle as a single equation, but there are actually multiple equations to find the area of a triangle. base times height times 1/2 just happens to be the most classic one to work with because all I need are two sides of a triangle and I can figure this out. However, sometimes we're not given the two legs of a triangle. We know displacement is 1/2 the change in velocity over time, which is the height times the base. But acceleration is the change in velocity over time. And I need to be able to describe the displacement in terms of acceleration because I want to be able to predict the future. If I have to wait to find out what the final velocity is, I have to wait to the very end to make a prediction. So it's kind of like if someone, after the very first book of Harry Potter, would say, ask someone else, hey, how do you think this is all going to end? This looks really interesting. How's it all going to end? And their reply is, well, I'll tell you what, I'll wait for them to write all the books. I'll read all the books. And after I read the last page of the last chapter, I'll tell you how I think it's going to end. You're not predicting. You're waiting to the very end to see what's going on. I want a prediction right now, and I want it to be accurate. So we have to rewrite this equation in such a way that we can predict the future. And we can do that by means of replacing the change in velocity with acceleration. Now I can't just do that willy-nilly, but I can take the change in velocity and divide it by time. That does not violate any mathematical rule as long as I undo the division by multiplication. So if you notice, I now have velocity divided by time, the change velocity divided by time, but instead of just time over here, I have time squared. Now, if you're thinking, Mr. Furlan, this time squared cancels out with this time, so I'm left with exactly what I have up here, you're totally correct. That's the point. I don't want to change the actual equation or its values. I'm just trying to rebrand it a different way. But here's the thing. Acceleration is the change in velocity over time. I can now replace this with the term acceleration instead. So I'm rebranding the equation so it looks differently. So once I make that substitution and rename this, I come up with the equation displacement is equal to 1/2 my acceleration times my time squared. So all I need to know is the acceleration in the very beginning and how much time it takes, and I can predict what the change is going to be. This is a far more useful equation than 1/2 change in velocity over time, because for the change in velocity, I have to wait for the motion to be over to actually know what's going to happen. Here, I can now make a prediction. If I look at more complicated motion where the object starts not from rest but with an initial velocity, then I also get a straight line, but instead of the area being a triangle, I actually now get to form a trapezoid because I will have to go down to the time axis. So it's this entire region underneath the graph. So I have a trapezoid instead of a triangle. Now, trapezoids can be a bit of a hassle, but I have learned never to work with a trapezoid. In fact, I always say trapezoids are a trap. I always break a trapezoid into two geometric shapes. It is a triangle resting on top of a rectangle. And those are two geometric shapes that are very easy to work with, especially for finding the areas. The area of the rectangle is always just height times base. So that would be my velocity times time, my initial velocity, because that is the height of the rectangle. For the triangle that's up on top, that's just going to be 1/2 AT squared. So I can easily say that the displacement for an object that starts with an initial velocity is equal to its initial velocity times time plus 1/2 its acceleration times the time squared. And the only requirement for this is that the acceleration remain constant. If the acceleration is not constant, then calculus is required, and that is outside our scope. A lot of times we're interested in not just the displacement, but rather the final position. And since displacement is the change in position, we can replace displacement with change in position and solve for position final. So position final equals position initial plus VIT plus 1/2 AT squared. Please notice, again, I'm writing this opposite you would see in a math class. In a math class, your professor would want to see, or your teacher would want to see, y equals 1/2, well, we'll put it in physics terms. Position final equals 1/2 AT squared plus VIT plus position initial. This way you know that right away that this is a quadratic, and you can now use all the properties of a quadratic formula to solve the problem. We don't care that's a quadratic. We care this is a position graph, and a position should equal positions. So right away I can see position is equal to positions. So that meshes, that makes sense. Plus velocity times time. Well, that's a displacement. So that's a change in my position. Plus 1/2 AT squared, which is another displacement. So my final position is equal to my initial position plus the change caused by my initial motion plus any change caused by the acceleration. So that's how we write this down. Now, you do not need to have this equation memorized. We give you this equation, so you just have to know how to use it. And so life is going to be pretty good. This is really the only position formula that you need because this covers all scenarios. If I go back to the case on where I have no initial velocity, so this doesn't exist, then my initial velocity is 0. This goes away. And I just have the triangle. If I'm looking at a case where I have no acceleration, well then my initial velocity runs as a constant velocity and there's no triangle. In that case, I have no acceleration and I'm left with the equation for just velocity times time. So no matter what's going on, I am set. If they ask me for displacement, they don't want my final position, but they want my displacement. An easy trick is to say, well, since displacement is the change in position, my initial position is 0, which making my final position automatically the displacement, because that is going to be the change in position from 0. Another equation that we'll be working with is known as the time-independent formula. The origin of this equation comes from both the position equation and the velocity equation that we've seen from the position graph and the velocity graph. Long story short, if I take the velocity equation, manipulate that to be set equal to time, where we can now say time is equal to the change in velocity over acceleration. And we plug that back into the position formula for time squared and time. We can actually derive an equation which is v final squared equals v initial squared plus 2a change in position, or my final velocity squared is equal to my initial velocity squared plus 2 times my acceleration timing the displacement. This is called the time-independent formula because if you notice, there's no time in the equation. This is very useful because there are going to be cases where no one was with a stopwatch. We have an object that slid across the floor. No one measured the time, but we need to know how fast was it moving or how far is it going to slide before it stops, but we don't know the time. So this formula gets you there independently of the time. Now, one of the things that is going to be overwhelming for people is all of the origins of the math. Now, we don't have to overcomplicate stuff here, okay? We are not interested in the mathematics that makes the equations. You will be provided with at all times these two equations as well as this bottom one. If you're going to write them down on a sheet of paper and just memorize, 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 flashcard these, you're wasting your time. On any quiz, on any test, they will be up on the board or they'll be on a piece of paper that you can use as a formula sheet. For any homework assignment, for any lab, they should be there. Now, my personal suggestion is perhaps for your notebook, you have like your first page or the very last page. You write down all of the equations just as a quick go-to so you don't have to look through your books, but no one is ever going to have you have these memorized. If you're taking the AP test, they give you these formulas. If you are taking a college class, I took several. I never had a college physics class in all of my years and all the different levels I took where I was told you are not going to have a formula sheet. You have to have every equation memorized. Now, there is a trap with this. Knowing the equation and understanding the equations are two different things. We will provide you the equations because there is no merit in knowing the equation. You have to understand what they are telling you. You have to understand how they operate. You have to understand how to use them. That is more in depth. That is where people get tripped up. So if you notice, we spend a lot of time talking about what these things represent because that's where your focus needs to be. It is easy to get tricked up with this stuff because of all the math. And then you think, okay, I don't understand all this almost calculus stuff. I don't like trapezoids. I'm all messed up. Don't overcomplicate. Use the tools that we provide, but you have to focus on the understanding. The math can be a distraction. So it's kind of like the analogy here of driving a car. We want you to drive a car. We want you to drive it safely and correctly. And to drive a car, you do not really need to understand how the car is built. There's the saying. Right now, we are discussing about the process on how we build the car. We're talking about the process behind the math that creates the equations that we work with. However, your real goal, our real focus is this part here, knowing how to drive the car. Can you use the equations properly? Do you know when it is appropriate to change lanes and when it is not appropriate to change lanes? That is what we're talking about. So we have our big three equations. As I said, they will always be given to you. So you just have to know how to drive them. You do not have to know how to derive them in math. You just have to know how to drive them in terms of using them like you would a car. I find naming the equations makes things a little bit easier. This way, instead of trying to rattle off an entire equation, you can just say, yeah, I'm using the position equation. I'm looking for the position equation, which would be the position final equals position initial plus VIT plus 1FAT squared. I name it the position formula because you're looking for position. Easy enough. For the equation that I use to find velocity, I call it the velocity equation. And for the one that has no time in it, it's independent, then I call that one the time independent equation. If you take a look at other physics books and you go off and ask physics tutors, about the time independent formula, they're going to just raise their eyebrow going, the what? Because these aren't official names. I find them to be very practical names, and so I decided to just use them. Now, a problem-solving strategy that you may want to use, and you're not required to use it at all, is known as a want-no equation table. Basically, what you do is you will tabulate out what you want. What are you looking for? What are you being asked to find? And when you're answering that question, answer it in the terms of position, velocity, acceleration, or time. That is what you're looking for because that's what the equations are that we work with. Then identify the stuff that you know. This is information that they give you or information that you might already know because of the situation. All right, and again, this would be positions and velocities, times, accelerations. Then you have your big three equations, and you're going to just focus on which equation answers what you want. So if you are looking for, let's say, time, I would not want to look at the time independent formula. I would just simply ignore that one and look at the other two. Then I would look at what do I know? And if I do not know the final position, but I do know final velocity, I definitely would not be using the position formula because I can't use it. I don't have position final, so I can't solve for time. I would have to use the velocity formula instead. If you're able to just solve the questions without this aid, you are more than welcome to do so. But if you are stuck, then use an aid like this. It can often help. There's always also what I call the Homer-Simpson method. You could just try out the top equation, and if it works, go woohoo. If it doesn't work, go dope and move on to the next equation. If it works, woohoo. If it doesn't, dope and just move on to the next equation. It's just really simple like that. There's only three equations, so you don't have to try it too many times to find the correct equation. Personally, though, I just use the want no equation table if I need to, because it does make my life a little bit easier. So, for example, let's say I have a scenario where I have a box that's being lifted from rest to a speed of 20 meters per second in 5 seconds, and I want to find the acceleration of the box. Now, the term from rest means the velocity is 0. If you're resting, you're not moving. So if you come to rest, you stopped. Your final velocity is 0. If you start from rest, then your initial velocity is 0. So I'm going to first fill out my want no table. I want acceleration. I know my initial velocity is 0. I know my final velocity is positive 20 going upwards because they did use the word lift, so I have a sign for my velocity. It was 5 seconds, and I was started, well, they didn't give me a position initial, so I'm calling it 0. And now I'm going to select what equation works best. Well, I want acceleration, so if any of those three do not have acceleration, I'm going to cross them out right away. And all three have acceleration. So I can't cancel anyone out. I'm in a very good spot because I can use pretty much anything. Everything has what I'm looking for. But now it comes down to what do I have? What do they need? Now, if you notice, I know V initial, I know V final, I know time, I have position initial, but I don't have position final. And since I don't have position final, this equation definitely is not going to work. Neither would this one. It's like when you go to a store and all you have is a credit card and they say, I'm sorry, we don't take credit cards, all we take is cash. You might have the financial means, you just don't have the tools to get what you want from that store. So going there is a waste of your time. So that's what we're doing. We're just allocating out which equation has what I want, which one am I capable of using. So since that velocity equation is the only one that I have available to me, that's the one I'm going to use. And I can find the acceleration. Please notice my acceleration is positive, which means it's moving upwards. Here I have a situation where I have a box that's being pulled from rest across a rough floor. It has an acceleration of positive 3 meters per second squared, or 3 meters per second per second. I want to find out how far will the box, that should be box, move in 10 seconds. So what am I looking for here? Well, I'm looking for how far. Well, what does that mean? I'm looking for the terms position, velocity, acceleration, or time. And how far something is relates best to a position. So I'm looking for a position, specifically position final. So position final is what I want. What do I know? I know it started from rest. I know it went for 10 seconds. I know the acceleration was 3 meters per second positive. And they didn't give me a starting position, so I'm going to turn around and say my starting position is 0. And please notice, I'm not really looking for final position. I want to know how far it traveled. So how far from my initial position. So I can pick any number I want. 0 is just the most convenient for me. So here I'm looking for position final. So this equation automatically is eliminated because it doesn't have what I'm looking for. I want position final. It doesn't offer it. If I want to go get a ham sandwich, I don't go to an ice cream parlor unless they serve ham sandwiches. And since I have yet to find one that does that, I don't do that. Okay? So now I am going to use one of these other two equations. But which one? Well, I notice that I do not know position final. This guy requires position final. So this one doesn't work. It's not the equation's fault. I just don't have what it's looking for. So it won't work. So the only thing left is the position equation. So that's the one I'm going to use. So now just by going through straightforward math and use of the equation, I can find that the position final of the object is 150 meters. That's 150 meters from where it started, so the distance pulled was 150 meters. All right, that's going to wrap us up here. I know there was a lot of stuff here. As always, we're going to go over this again in class. We're going to apply what you have seen here. So if you went through this and you're getting a good understanding of it, you're in a very good place to be. However, if you are having questions, that's totally okay. We are going to address all those in class. And if you are confused on this material or feel overwhelmed, that's all right. We have plenty of time to work on this. And as always, these movies are not to get me out of actually teaching in class, just to give you exposure before we talk about this in class.